Hey guys, welcome back to the channel. Got an interesting video here for you guys. And first thing I'll say is it's kind of a technical video. It's going to be kind of long and it might be kind of dry. So unless you're really into these types of things, you might not make it very far into the video. Okay, so the problem that I have actually revolves around the surge tank that I installed on the car. And here we've kind of got like a diagram of how everything was electrically connected. The issue is that when I trigger this relay, it's running my surge tank and my in-basket fuel pump, both of these pumps, at 100%. And it's just ramming fuel towards the motor. Now, for an EJ, that's not a problem because EJ motors or the fueling system in an EJ motor has a return line. So any fuel that isn't being used at the motor is coming back to the fuel tank. On an FA, we have a returnless fuel system. So if you keep shoving fuel to the engine and the engine isn't using all of that fuel pressure is just going to build up and build up and build up. And at some point, that pressure is going to overwhelm the high pressure fuel pump. And now that high pressure fuel pump's pressure is going to go up and go up and go up. And the car will slowly start to run more and more rich. I mean, the ECU has some ability to control kind of how the injectors are firing to pull fuel out of it. But at some point, it's going to lose the ability or run out of adjustment. And the motor is just going to go pig rich. So this is not a feasible system for a car that may see stop and go traffic or may end up idling for some period of time. Because even though we have a fuel pressure regulator on the surge tank, you run this pump at 100% long enough, that regulator is not going to be able to keep that pressure at, say, 55 psi. Okay. The other problem is that if you look up the Subaru fuel pump controller and most fuel pump controllers, you'll find out that these fuel pumps run on a PWM signal. And that stands for pulse width modulation. And I'm on good old Wikipedia here. And there's a lot of information here that I don't understand. But from what I gather, the gist of it is this bottom line here is when the signal is at 0 volts. And this top line here is at when the signal is at its maximum voltage. And so let's just arbitrarily say that's 12 volts. And to control the pump, what happens is you pulse the signal on and off. So typically in a lot of the older cars, you'll just run them at like 8 volts. And then if you want the pump to run harder, you might increase the voltage to like 10. And if you want it to pump even harder, you increase it to 12. Something like that. Or maybe you run it at 100%. But apparently PWM is more efficient and a better way of controlling a fuel pump. And so a lot of cars are moving in this direction. So they're moving in this direction, or they have moved in the direction of pulsing a voltage to the pump to be able to control how fast or how much it's pumping. And the most important thing to know is you've got the 0 volts, and so let's say arbitrarily say this top line at 12 volts. And to get the pump to pump more, you just increase the duty cycle. So when it goes from 0 to 12, how long it stays at 12 is the duty cycle in a given period, a given time frame, right? So 50% duty cycle implies that it's on 50% of the time and off 50% of the time. And if you want a greater duty cycle so that the pump sees that 12.2 volts or 12 volts longer, so it pumps more, you increase the period or the time that you're pulsing the on or the 12 volts. So here you can see that this distance is longer, or this distance is longer than this one, and so this duty cycle is more, right? And you can see that here, 75. And if you want the duty cycle to be lower, the time that you're pulsing the 12 volts is shorter. So in this case, see this distance is much shorter, and that's a lower duty cycle. So everything that I've read shows that Subaru fuel pumps have 3 modes: low, medium, and high. And originally someone asked me to talk to iWire, because they've got a wiring harness that says it retains this fuel pump controller's low, medium, and high setting, which I can't find here, but I read it earlier. Here we go. Low, medium, high. But they also tell you that it doesn't work for the WRX or the 2015 WRX or 2014 Forester. And I spoke to them, and they actually said, yeah, this harness, for whatever reason, we've tried it with the FA motors and the Hitachi ECUs, and it just doesn't work. So we don't have a solution for you. So that went out the window. And so my solution, after searching around, was to use a solid state relay. And these have been used in cars before. I think people use them to trigger like NOS systems. Cyvex, which is I think like a standalone ECU, recommends using a solid state relay, and Haltech recommends using a solid state relay. They're really good. They do have some limitations, right? So if we think about pulse width modulation, this is duty cycle, but there's also frequency. And one of the limitations of a solid state relay is the frequency that it can run at. So you can see here, depending on which relay you get, there's a maximum frequency that you can run it at. And unfortunately, no one seems to know what frequency these fuel pumps run at. So I talked to my buddy Nathan Gorwitz. I hope I'm pronouncing that right. I apologize, Nathan. And he suggested I get an oscilloscope, which is kind of an expensive tool, but given no one knows, it was worth hooking up an oscilloscope to see. So if you can refer back to this diagram, we're going to tap into, what I did was tap into the trigger wire for the relay, which comes off this factory fuel pump controller, which is this wire, number 6, I think. It's the green and yellow wire. Tapped into it, hook up the oscilloscope, and boom, we got this picture. And this looks nothing like this. So this is the signal or the waveform that we're expecting to get from a car that is outputting a PWM signal. And I can use the access port, or I did use the access port simultaneously to pull up the fuel pump duty cycle. It was sitting at 71%, and at 71%, we want to see something very close to this shape, and we're not seeing it here at all. I don't know what these little dips are, or these little peaks are, but the shape of what we're expecting to see isn't here. So that actually threw a wrench in my what I thought I was doing, right? So I kind of went back and I was testing this around, and what I was doing was turning the car on, and when I first turned the car on, it would switch to high mode, and in this case that was about 88% duty cycle, and then after a few seconds after turning the car on, it would then switch to medium duty cycle, which was 71%, right? And if we remember what duty cycle is, it should be a constant voltage, and just all that matters is how long we keep it off in relation to how long we keep it on, or how long we keep it on in relation to how long we keep it off. And what I was seeing in the oscilloscope was that the voltage was actually changing, right? So if it's supposed to be 12 volts, right, what I should have seen is 12 volts, and then the width of these squares changing in relation to one another. But instead, I was seeing this line, this horizontal line, go up and down. So right here, I think it's like my scale's 10, so this is about 12 volts. And I was seeing the voltage at like 14 at 88% duty cycle, and then the whole line would drop down to like 10 volts at like 71% duty cycle. So I'm starting to think that the fuel pump controller, at least the wire coming off the fuel pump controller to the fuel pump, is not a PWM signal. And it's just like an analog signal that ranges between 6 volts and 18 volts, because that's the spec that the AEM 50 1200 can take, right? 6 minimum, 18 maximum. And if I look at this wiring diagram, I can see 2 wires coming to the fuel pump controller, and I'm wondering if one of these wires is actually the PWM signal. So the PWM signal comes into the fuel pump controller, and the fuel pump controller then takes power off this relay and then powers the fuel pump. And so that, if that's true, I actually have 2 options here to fix my problem of running the fuel pumps at 100% duty cycle. I can't wire up the pumps in series because the gauge of the wire is just not designed to carry the current needed to run 2 pumps. So I still need to run the pumps off the battery, but there's potentially an option where, I take the input voltage and then spit it back out using some type of voltage regulator off of the battery. I'm not exactly sure what that part would be called, and I've done some Googling and I can't find anything like it. So I think there's a knowledge gap there. I just don't know what I'm looking for, and I don't know what it's called. And the things that I have found don't work in the range of 6 volts to 18 volts. Okay, so if that's a problem, and I can't find anything off the shelf that's like that, then I've got to go back to the PWM signal. Hopefully, which I'm going to test tomorrow, hopefully we can get a PWM signal that matches the change in duty cycle that's coming off the access port. If one of these is a PWM signal that we're expecting to get and it matches the duty cycle changes I'm seeing on the access port, we can use the solid state relay. However, and I already bought this relay and it's sitting downstairs. However, the problem with this relay, although it's recommended by companies like Cyvex and Haltech as a solution to run fuel pumps, is that if relays like these fail, they kind of tend to fail catastrophically. They like smoke, they potentially shoot out flames, like it's pretty ugly. And that's probably not something that I want to have in the back of my car near a bunch of fuel lines. So I did more searching, and my dad, who's an EE, electrical engineer, suggested I look up DC motor drivers. And I came across this website called Dimension Engineering, and they've got a whole bunch of motor drivers that are actually designed for battle bots or battle robots. And here's an example of one. This is a dual motor driver that can drive individual motors at 25 amps continuous, which is more than enough for the fuel pumps that I'm running. They can output the correct voltage. They can connect to the battery, but more importantly is that, one, they have thermal protection and overcurrent protection, right? So if it's starting to get too hot or there's too high of a current draw from the motor, instead of blowing up spectacularly, the controller will just limit what's going on or turn off, right? Which is much safer. The problem is these types of controllers, at least all the ones that I've seen for BattleBots, they don't accept a 6 to 18 volt input signal or analog signal, and only accept a 0 to 5 volt, right? So what I'm praying for is that if I tap into this wire and I see a PWM signal that matches the duty cycle that I'm seeing on the access port, that it is only 0 to 5 volts. If that works, then I can just tap this wire, connect it to something like this, connect my battery to this, and then connect my motors to this. And this will perfectly run the 2 fuel pumps just fine. The only other thing that may be an issue is that I know that the car, whether it's the ECM or the fuel pump controller, when the motor goes to 0 RPM, the fuel pumps stop, right? And so what I think is happening is that the ECM recognizes that the motor is stalled, and it stops sending kind of like a signal to the fuel pump controller, and the fuel pump controller cuts the fuel pumps off or doesn't apply power to them. I want to retain that safety feature because in the event that I get in an accident and the motor stalls, I don't want the fuel pumps to be running at full bore and potentially squirting fuel all over the car if a line is broken somewhere. So this is sort of like my potential solution. I've got a couple other things I need to test in terms of the wiring on the car, and kind of trying to find the right signal. And if that's the case and I can find it, I will definitely get one of these DC motor drivers, and they've got a bunch of them here. I think there's one for like 30 amps too. And I think that would be my solution, and I can get rid of the solid state relay, because I think without any sort of protection, the solid state relay may not be the best idea. Otherwise, if none of these signals pan out, I've got to figure out a way to kind of amplify the voltage coming off of the fuel pump controller. Again, because the wires aren't the correct gauge to provide enough current to pumps, I need to find a device that'll take the input voltage and just simply regulate the voltage that the pumps are seeing coming off the battery. I don't know what that's called, so I'll have to try to find something and hopefully not have to like build something, because using the oscilloscope is already complicated enough. Building something would be, at that point I think I'm like SOL. So that's where I'm at with this surge tank. Admittedly, I really have bitten off more than I can chew, and I'm sort of in a bind because I don't think anyone's really done this in an FA car, or at least done it where they want to retain this changing of duty cycles instead of running it at 100%. Yeah, so hopefully the next video I'll have a solution up and running for the car, and it'll be all great and dandy. We can go to the tuner. Yeah, and I think that is it. Before we go, I want to thank a couple of people who have been working through this problem with me. First one's going to be my dad. He is an EE, but I think he's a little out of practice. But he's been a really good sounding board in kind of like checking to see whether or not I'm looking at things correctly. I want to thank Nathan Gorwitz. Hopefully I'm saying your last name right, man. He's been a great gut check as well, and sounding board, and was actually the guy who recommended that I get an oscilloscope to see what the hell is going on. And although I'm probably not using the oscilloscope to its maximum potential for what it's capable of doing, it is the one tool that's going to help me identify what's going on in this circuit. And I don't think I could potentially find a solution without it. So Nathan kind of like kicked me in the butt and said, look, you need to get one of these because it's the only way you're going to really know what's going on. And then the last guy is Simon. Simon, I think, is an electrical engineer, and he's also been a great sounding board. Was sending in pictures of the waveforms that I was getting, and he was like, oh, I don't think that's right, or that's not what we're expecting. And even offered up to do a little video chat here to kind of work with me with the oscilloscope in the car to kind of understand what's going on. So I can't thank these 3 people enough, because I am way outside of my wheelhouse, and without the help of these individuals, I'd be pretty much down a really, really dark hole, spend a lot of money, and have no solution for the car. Yeah, so that's it. So hopefully next video here in the next week or two, depending on what happens, we'll have the car running and I can kind of show you what we did to fix the Subaru. If you guys have comments or questions, or if you know of any potential solution, please don't hesitate to share that with me. I would really appreciate it. And I think that's it. So we'll see you at the next video, guys. Thanks for watching. Take care.